Okay, welcome students. We are now in day 2 of the new unit, part 2 of the unit that I ended up kind of splitting up for the sake of keeping things kind of concise and at a decent amount. Now, if you see here, just some updates. Again, we've got vocab article assignment should have been completed already. We've got the, again, online tests, which are currently being completed now. So hopefully you guys have those done. And then again, we'll have other activities that are different from the classes in person that you see listed above up there. As for our Go Blue, number 1, the other day we talked about NASA, some different spacecrafts that are being used to explore deep space. So let's get into that with our Go Blue today. On page 4, we're on page 4. Number 1, what NASA space telescope, let me see if I can see it on my screen here. Okay, so what NASA space telescope records HD images of deep space, so high definition images? It is now retired, but it was used for many, many years, starting in 1990. 2, what does this telescope use to record these images? And 3, it's a fill in the blank. Blank are planets that orbit stars outside of our solar system. Let's go ahead and pause the video, see what you think. Write those down on page 4. Let's go ahead and move on to our answers then. With number 1, we've got the Hubble Space Telescope being the first major spacecraft we get into. It's taking some of the greatest and the first images of deep space, the Hubble Space Telescope. Okay, and then number 2, we have here, how does it take those images from deep space, those amazing pictures that we've seen in all of our textbooks and in many movies? We're going to be using massive mirrors that are, again, as massive as you see in this picture compared to the size of a human. So very large. I'd say maybe the length of, looks like almost 20 feet maybe. So pretty massive there, 20 feet mirrors. And then number 3, we've got exoplanets, being those planets that are outside of our solar system, exoplanets. And we watched that news video yesterday that kind of went into that. That was pretty cool. Okay. So moving on from there, we've got our table of contents. We're going to get into some laws that are involved in space, some space laws. We've got 4 and 5. Again, we're on page 4 right now, being Kepler's laws of planetary motion. The laws of planetary motion are going to be on page 5. It's going to be the title of page 5. Again, Kepler's laws of planetary motion on page 5. And then we got 6 and 7, Newton's laws of motions. We'll get to it at a later time. Okay. Moving on to our first question of the day. Again, pause the video after I ask the question so you can test yourself. What is the hottest planet in our solar system? Hottest planet in our solar system. Is it A, Mercury, B, Mars, C, Jupiter, or D, Venus? What is the hottest planet in our solar system? Pause, see what you think. Answer is going to be D, Venus. Guys, again, Venus is the second farthest, the second closest to the sun, which makes us ask, why isn't Mercury the hottest? Well, I think Venus has a lot of different gases and it has a lot of carbon dioxide and volcanic activity, which actually makes it a lot hotter of a planet. Okay, real quick, guys, I'm going to show a video. We saw the news video yesterday, so I'm going to show another clip. Ask us, what if we found and discovered another Earth? And the question is going to state not how, man. It should be, we know we have the Kepler spacecraft, right? Looking at a lot of different outer planets that are outside of our solar system. So I want to know specifically, just given a number, how many exoplanets has Kepler discovered so far? How many exoplanets has it even discovered so far? Let's go ahead and write that down on page 4, and let's go ahead and check this out. Again, I may not play all of this video. I'm just going to play most of it. I may post a link if you want to watch the entirety of it.
Could there be an even better planet for us than Earth? Scientists are searching for a super habitable world that wouldn't just rival Earth, but be a place where life could thrive even more easily. And they're looking at exoplanets.
Right, Kepler.
How would we discover Earth 2.0? What would make an exoplanet habitable? And how long would it take to get there? This is What If, and here's what would happen if we discovered Earth 2.0. You wouldn't be able to find an exoplanet by looking through a telescope. all you'd see is the bright glare of the stars they orbit. NASA built the Kepler telescope to discover exoplanets. And before it ran out of fuel, the Kepler telescope surveyed our region of the Milky Way galaxy. Its technology uses the transit method to find planets hundreds of light years away. How? It measured the fluctuation of light coming from distant stars. When a planet transits or passes in front of a star, the star isn't as bright, so the Kepler telescope uses that to detect exoplanets. This is not an easy thing to do, but during its 9-year lifetime, the Kepler telescope confirmed the existence of 4,367 exoplanets. Could any of them be Earth 2.0? If you're a longtime fan of What If, you've probably heard this before, but Earth is a very special place. And even if a planet is deemed to be habitable, it doesn't mean that it resembles Earth very much. A habitable planet is a rocky planet located in the habitable zone, allowing water to stay on the planet's surface in its liquid form. That's it. Venus and Mars are habitable planets, but they are definitely not like Earth. So let's talk about 3 major conditions that we'd look for when searching for an even better version of Earth. First, it would need to have sunlight. Our sun's lifespan is about 10 billion years, and it took 4 billion years for anything more complex than the simplest life form to pop up on our planet. But K-type dwarf stars have lifespans of about 70 billion years, so if we found an exoplanet orbiting a K-type star, there would be more time for life to evolve and live on it. The second major condition is temperature. A planet that's too hot or too cold wouldn't be able to host the life forms we'd need to survive. But if we find a planet that's a mere 5 degrees warmer than Earth, and it has more water, we could be looking at Earth 2.0, covered in a lush, biodiverse rainforest. The third major condition we'd be looking for is size. Gravity retains a planet's atmosphere, and there's a direct relationship between gravity and a planet's size. So if we find a planet that's only 1.5 times larger than Earth, it would be able to hold on to its interior heat and maintain its atmosphere for a longer time. But bigger isn't always better. While Earth-sized exoplanets are usually rocky, about 50% of the exoplanets larger than Earth are gas giants. And if an exoplanet is too small, it would likely be barren, like Mars. So, are there any exoplanets out there that meet these requirements? You know, all this comparing data and gathering information is starting to make my head hurt. I wish I could just enter everything into one piece of software and we could see which exoplanet could be Earth 2.0. Instead,
I see
have to
that
sift
we've
through
got
spreadsheets and confusing software. If you run a business, then you know my pain, but
looks like we've got a little advertisement in the middle of our video today, but I think they made the main points. There are potentially likely other Earth-like planets being discovered because they're in that golden zone.
There wouldn't be any seasons on Kepler 1649.
Okay.
What are you doing on your phone?
So I'm sorry, advertisement. We're going to move on because of time, but as you can see, there's a great possibility of other Earth-like planets that we're discovering right now that likely have ice, water. 4,000 planets, guys, 367. Okay. And massive. I mean, you're talking billions and millions and billions of solar systems, the endless amounts of planets we can discover, and the endless amounts of other Earth-like planets. It's just, again, it's a matter. It's mathematics. It's just a high possibility, right? And we're already seeing that today. Let's go ahead. Let's continue. And that number is only going to keep increasing with the Kepler spacecraft. Real quick, I want you guys to go to page 5. I'm just going to show the first law today because I am limited on time right now. I'm trying to pre-record lessons instead of the live ones because I think it's just easier. You guys can hear me better. I don't have to wear a mask, right? because there's no one in the classroom. Let me go ahead. I got them. This is in the way. One of those days, I guess. Okay. So we all have things happen during the day that we, have to work around, right? Okay. So let's go ahead. I want you guys to go to page 5, and we're just going to write down Kepler's first law of motion and call it a day. Okay. So planets move so again, there's 3 things we need to know about how planets move. Okay. About like in regards to the shape of the movement, the speed, and all that, right? So the 3 laws on page 5, title it Kepler's first law of planetary motion. And I want you to say this: planets move in an elliptical orbits with the sun at one of the foci. Okay. Again, as we can see here, planets don't move they don't orbit in a circle. They move in this longer oval shape. Okay. And the sun usually is not going to sit at the center of that. Okay. The sun's usually going to sit at one end or the other, right? Okay. So that's going to be first law of motion. First law of motion. So planets move in elliptical orbits with the sun at one of the foci. Okay. And if I think, another thing I want you to add to that, guys, I want to talk about 2 new terms, 2 new kind of vocab or terminologies I want you to know in regards to this orbiting. So make sure you wrote that for law number 1 on page 5. Okay, yeah, and there's the sun. The sun's right there. Just write what's in red, by the way, just what's in red. Again, this is below law number 1 on page 5. Aphelion. That's where the object is farthest away from the sun. Okay, so aphelion would be this point, the very end of the ellipse, where, again, the object is farthest from the sun. Okay. Then we have the perihelion as it rounds about. That's the end where it gets closest to the sun. Perihelion, right? So again, aphelion, where it's farthest from the sun in the orbit. Perihelion, where it's the closest. Okay. And just to emphasize that further, let me see if I had a video clip. Okay. And I think I'm going to go ahead, and because of time, I'm going to save that for another day. We'll get to that probably tomorrow. Okay, let me go ahead and show our last question then. Okay, blank is the first planet inside the asteroid belt, while blank is the first planet outside the asteroid belt. Is it A, Mars, Jupiter, B, Mercury, Jupiter, C, Mercury, Saturn, or D, Jupiter, Mars? We're talking about the planets that surround the asteroid belt. Okay, it's going to be, guys, pause the video, see what you think. And it's going to be, guys, letter A, Mars and Jupiter. Mars and Jupiter. Okay, Mars, Jupiter. All right, so keep that in mind. Keep that in mind. Okay, that is it for class today. We'll continue. We'll finish page 5, Kepler's laws of motion or laws of planetary motion in our next lesson. And I think we'll probably look to start and begin Newton's laws of motion. This is Mr. Campbell signing out.